Hello, my name is Juhan Park. The paper I'll be presenting for today is a machine with short-term, episodic, and semantic memory systems, which was accepted to AAAI conference in the year 2023. Before we get into details, I'd like to introduce how memory is categorized in the human perspective. Based on the cognitive science theory, human memory can be categorized into semantic memories and episodic memories. Semantic memories refer to the factual memories such as the name of one's brother. It is generally not followed by any momentary information, such as when and where the memory was acquired. Episodic memories, on the other hand, are the memories of personal experiences, such as the latest meal you had today. It typically goes together with momentary information, as it is directly related to the time and place it occurred. Nowadays, AIs have shown remarkable progress as they often exceed humans in question answering of general knowledge, which can be categorized into semantic memories. However, in contrast to semantic memories, AI systems suffer when dealing with episodic memories. This is because the memory systems of AIs are not designed for such memories. And considering that AI applications such as personalized assistants and recommendation systems rely heavily on the personal memories with the users, the need for a comprehensive memory system that supports both episodic and semantic memory is growing rapidly. The work of today's paper directly addresses this issue. They modeled a human-like memory system that supports various memory forms including short-term, episodic, and semantic memories. Additionally, the authors designed an environment where the agent can learn to manage its memories and be evaluated on its performance. Before diving into the memory systems, I'll first explain how their environment is configured and how it interacts with the agent to facilitate its training. The environment is a single room whose status is modified by events occurring in discrete time steps. For example, we would have time step values of 1, 2, 3, and so on, each followed by a certain event. The room is basically occupied with humans, objects, and possible object locations. For example, we may have Alice and Bob as the humans, laptop, hat, and phone as the object types, and desk, closet, and chair as the possible object locations. The events in each time step are caused by the humans in the room, modifying the state of the objects. Their states are represented using ConceptNet's knowledge graph structure, which is formatted as a three-dimensional vector of head, relation, and tail. The below image provides an overview of ConceptNet's knowledge graph structure. You can see that the edge connecting the two nodes defines the relationship between the two. For example, if we took the dog node, park node, and the edge node connecting the two, we get ourselves dog and location in park, which states that the dog is located at the park. Using this structure, the humans in the room modify the state of the objects. At each time step, they move an object to one of the possible object locations. As in the left image, when the human named Alice moves her laptop to a desk, it would be represented as Alice's laptop at location desk. Note that the simulation only allows the human to move his own belongings, meaning that Bob cannot move Alice's laptop or vice versa. Also, every human in the room follows a fixed routine and repeats it until the end of the simulation. For example, Alice may be configured to have the laptop on the desk for 2 time steps and on her lap for the next 3 steps. The routines of the humans, however, may not work as planned, as the authors added probabilistic features into the process. Remember that the ConceptNet provides a graph regarding the relationship of the entities? Well, the graph in fact also has weights applied to the edges. For example, the laptop entity may be connected to the desk entity and the toilet entity using the same at-location relation edge, but the weights applied to the two edges can be different. Because laptop is more likely to be placed on the desk than the toilet, the at-location edge connected to the desk entity has a higher weight assigned to it than the edge connected to the toilet entity. Based on such features, the authors searched for the most relevant entity, also referred to as common sense location, for each entity and assigned the probabilistic value of p common sense. If a human following a routine is attempting to place an object onto its common sense location, the probability of success is p common sense and 1 minus p common sense for other locations. For example, if a desk entity was found to be the laptop entity's common sense location and p common sense was given the value of 0.7, Alice's attempt to place the laptop on the desk would have a 70% success rate, while the chance of placing it on her lap would be 30%. If the placement failed, the object would be placed onto some other random location. In the environment settings, the authors set the p common sense to 50%, claiming that it helps avoid biases. The room environment then interacts with the agent through the following steps. The knowledge graph generated by the human is concatenated with the time step to be given as the observation result to the agent. The agent processed the observation using its memory system, and a question regarding the state of the previously observed object is given to the agent. The agent uses its memory system to generate an answer and receives feedbacks based on whether the answer is correct or incorrect. Now that we've understood how the room environment works, let's find out how the memory system of the agent is designed. The memory system of the agent is divided into short-term memory and long-term memory, with long-term memory further divided into episodic and semantic memories. You might have noticed that the format of the semantic memory is slightly different from those of short-term and episodic memories. This is because semantic memories store factual information, which implies how likely it is for the head entity to be in the given relationship with the tail entity. The strength value indicates the likelihood and is derived from the number of times the agent has decided to store the memory into the semantic memory system. In addition, the name of the individual human no longer appears in the semantic memory, as factual information does not necessarily relate to a specific individual. Every observation received is initially stored in the short-term memory system. When the system gets full, the agent chooses from the three options to handle the oldest memory: forget it completely, move it to episodic memory, or move it to semantic memory. Because there is no straightforward method to numerically define the algorithm, the authors adopt a deep Q learning method. Deep Q learning is a family of reinforcement learning which aims to train an agent to execute optimal actions for the current state in a way that maximizes the rewards received. In case of Q learning, the goal is to find the Q value function, QSA, which represents the expected total reward for taking action A in the state S. For example, if we had three action options, A0, A1, and A2, and QS, A1 return the highest Q value, the A1 action will be chosen as the optimal action for the given state S. The deep Q learning leverages a deep neural network to approximate the Q value function. In this case, the input to the network is the state S, and the output from the network is a set of values for all A's. In our case, the state S is defined as the state of three memory systems and the action A comprising of forgetting, moving it to episodic, and moving it to semantic. Since the memory is in the form of a string, we first need to embed it into numeric representations for network processing. To do this, we initialize a learnable embedding vector lookup table called EMB, which contains all the embedding forms for every entity and relation in each of the memory system. This page here presents the overall pipeline for the embedding process. The memories are sorted based on the strength for the semantic memories and the time step for the short-term and episodic memories. Then the ordered memories are embedded using the lookup table EMB, and the embedding results are concatenated into a single embedding vector. After having applied the embedding process for the three memory systems, the outputs are fed into their respective LSTM networks and the MLPs. The results from the three pipelines are concatenated to compute the final Q-value. The Q-value is a three-dimensional vector whose elements map to the corresponding actions. The action with the highest Q-value is selected for execution. For each action, the reward is computed by answering the follow-up question. If the answer is correct, the reward value is 1, of 1 is returned, and 0 if false. The loss formula of the paper is built upon that of the original Q-learning. The image on the bottom right presents the loss computation of an original Q-learning network. The training consists of a base network written as Q network and a target network, which is a clone of the Q network. The parameters of the Q networks are not updated. The parameters of the target networks are not updated by the loss function, but by the periodic cloning of the Q network. The target network is adopted to stabilize the training process of Q network, as using the Q network for both the target value and the action value results in fluctuating target value during the parameter updates. The formula on the top of the image presents the loss function, which is the L2 loss between the target value and the action value. The target value represents the estimated return for the current action based on the immediate reward plus the discounted maximum expected future reward from the next state as t plus 1. The action value term represents the predicted value of the current state action pair according to the Q network with parameter theta. Minimizing the gap between the target value and the action value means aligning the predicted Q value with the actual Q value based on experience. The paper replaced the L2 loss between the target value and the predicted value with Huber loss, which is known to be more robust to outliers due to its switch to L1 loss when the error exceeds a certain threshold. The memory systems for long-term memories are relatively simple. The episodic memory system focuses on forgetting the oldest memory stored, and the semantic memory system prioritizes the removal of weakest memories. The retrieval of memories is done using long-term memory systems. First, we look up the episodic memories to retrieve the relevant memory. If there exist numerous relevant memories, the most recent one is chosen as the target. If there are no relevant memories in the episodic memory, we search inside the semantic memory system. It can be seen as like guessing what the answer would be based on the common sense knowledge. Now we move on to the experiments section. This page presents the basic setup for the various experiments conducted. First, the capacity of the short-term memory is fixed to 1. This means that the short-term memory storage handling process is done every iteration step. Second, the relation form is limited to at location only. The reasons are not explicitly mentioned in the paper, but I assume it's to reduce the complexity of the training. Third, the agent only observes one human at a time in a fixed order. This ensures the agent observes all humans equally often. And finally, the probability of previously observed objects appearing in the question is distributed uniformly. The first experiment is regarding the pre-filling of the semantic memory system. The authors prepared two setups where the first agent was initialized with an empty semantic memory, and the second agent had its semantic memory filled with knowledge brought from the concept net. The training results show that the pre-filled agent not only learns faster, but also converges to better optimum. This shows that while the semantic scratch agent struggles to learn the generalized memories from the trials, it shows limitations compared to the agent with the better start. The second experiment is about evaluating the reinforcement learning-based dual memory system agent. The comparison involves three targets: one that always transfers short-term memories to episodic memory, one that always transfers them to semantic memory, and one that randomly selects between episodic and semantic memory. The results show that the reinforcement learning-based dual memory system agent outperforms the others, regardless of whether the semantic memories were pre-filled. The third experiment examines the performance changes under extreme memory capacity settings. When the memory capacity is large enough to store all the iterations, the episodic-only memory achieves the best performance with a 100% accuracy rate on all questions. In case of limited memory capacity, such as with a capacity of 8, the semantic-only method performs the best, indicating that relying on common sense knowledge to guess answers is most effective strategy when memory is scarce. And although the paper didn't explicitly mention any limitations, I'd like to offer my thoughts on this matter. First, the exclusive use of at-location relation without incorporating any other types of relations was a bit disappointing. Given the wide range of relationships between entities, this limitation raises concerns about the robustness of the method. Second, the reliance on the embedding table significantly restricts the system's applicability in more complex, uncontrollable scenarios. It might be worth exploring the use of LLM models for generating vector embeddings, as LLM embeddings are known to capture rich semantic relations between the entities. Thank you for listening, and please leave down the questions in the comments.